learn like a pro.
Today, we are not just going to learn some physics. Nope, we are going to crack the code. We're going to take what looks like the chaotic world of moving objects and reveal the simple, powerful blueprint that's running the whole show. So how do they do it? How does a physicist look at something in motion and predict exactly where it's going to be? Is it some kind of magic? Absolutely not. It's a system, a repeatable algorithm. You see, motion isn't random chaos. It's just a puzzle. And by the end of this, you're going to have the key.
And here's our roadmap. We'll start with the 5 essential variables, the building blocks. Then we'll see how they fight it out in a vector tug-of-war. After that, I'll introduce you to a diagnostic matrix that tells you the right tool for the job. We'll test it all out on a free-fall problem, and finally, we'll assemble the complete universal algorithm.
All right, first things first, the raw materials. Every single problem that involves an object speeding up or slowing down at a steady rate, it's all built from the same 5 fundamental pieces.
And here they are. These are our 5 key players. We've got displacement, which is just how far something moves, initial and final velocity, how fast it starts and how fast it ends, acceleration, which is how quickly that velocity is changing, and finally, time. That's it. Every story about motion is written with just these 5 variables.
Okay, listen up, because this right here, this is probably the single most important rule in all of kinematics. 3 of these variables, velocity, acceleration, and displacement, are what we call vectors. That's just a fancy word meaning they have a direction. And the formulas, well, they're dumb. They don't know up from down or left from right. You have to tell them by assigning a positive or a negative sign. Getting this step right is absolutely non-negotiable. And that whole idea of positive and negative signs, that leads us straight to what I call the vector tug-of-war. This is where those little plus and minus signs come to life and literally decide if an object is going to speed up or slow down.
Think about it like this. When you slam on the brakes in a car, your velocity is still pointing forward, right? But the acceleration from the brakes is pulling you backward. They're fighting each other. That's scenario 2 here. And so you slow down. But what happens when you hit the gas? Your velocity is forward and the acceleration is also forward. They're on the same team, pulling in the same direction, and you speed up. It's really that simple. The direction of those vectors dictates everything.
So, we have our building blocks, and we get how they interact. Now for the really clever part of the system, the toolkit that tells us exactly which formula to use. This is where we stop guessing and we start being strategic.
And this is the core idea that changes everything. Seriously. The skill isn't memorizing a bunch of equations. The real genius is in knowing exactly which one to pick for any problem you face. And this is how we do it. This beautiful thing is the diagnostic matrix. So in any given problem, you'll know 3 of the variables, you'll need to find a 4th one, and there will be one leftover variable that you just don't know and don't care about. This matrix lets you use that one irrelevant variable to find the perfect formula. You just find the variable you're missing on the left, and boom, it hands you the exact equation you need on the right. It is basically a cheat code for physics problems. So what's the big payoff for using this? It's all about efficiency. It's about working smarter, not harder. You see, without the matrix, you might accidentally pick a formula that forces you to solve a messy quadratic equation. But if you consult the matrix first, you can find the smart way, the one equation that just bypasses all that nasty algebra and takes you straight to the answer. All right, theory's one thing, but let's put this blueprint to the test. Let's get our hands dirty and apply our brand new toolkit to one of the most classic physics scenarios there is, an object in freefall. Now, what's so great about any problem involving falling or throwing something up in the air is that the Earth gives you a free piece of information. The acceleration is always caused by gravity. We'll round it to a nice, clean 10 meters per second squared. And remember our vector rule? Usually we define up as the positive direction. Well, gravity always pulls down, so we give it a negative sign. A is always -10. It's a given.
And here's what that constant downward acceleration actually does. Just look at the pattern here. Every single second an object is falling, gravity adds another 10 meters per second to its downward velocity. It's not random, it's a perfectly predictable cascade. Okay, pro tip here. This is one of those hidden givens that can totally unlock a problem. When you throw an object straight up into the air, what happens at the very, very top of its flight? For just a split second, it stops. It hangs there before it starts to fall back down. At that one instant, its velocity is 0. The problem might not tell you that, but it's always true and you can always use it. Okay, let's put it all together. Check out the first thing they do here. They define their frame of reference.
Now, because everything is moving downward, they just decided to call down the positive direction for this problem. And you can totally do that. It just makes the math a little cleaner. They spot their hidden given, dropped from rest, means the initial velocity u is 0. And from there, it's just plugging the numbers in and executing the calculation.
So, we've looked at the parts, we've seen the tools, and we've watched it in action. Now it's time to assemble everything into the final master key, the universal kinematics algorithm.
And this is really the whole point. This isn't just a collection of random tricks. It is a single, powerful blueprint that you can apply to countless different situations.
And here it is, the whole system in 4 simple steps. Step 1, draw the system and define your positive and negative directions. Step 2, hunt for your 3 given variables and don't forget to look for those hidden ones. Step 3, consult the matrix to find the perfect equation. And step 4, execute the math. That's it. That is a blueprint for solving motion.
So we've taken the seemingly complex physics of motion and revealed the simple algorithm running underneath it all. It really makes you wonder, doesn't it? If this elegant blueprint exists for something like motion, what other complex systems out there in the world are just waiting for someone to come along and figure out the blueprint that makes them work?